Everyone, and welcome to the last day of Cyber Science 2021. Thank you for joining us. Our theme for today is AI-enabled social media innovative information operation. We have a day full of interesting talks and 2 keynotes, so I encourage you to join us for all of these. Our first talk for today is Unsupervised One-Class Learning for Anomaly Detection on Home IoT Network Devices by Jonathan White. To Jonathan, without further ado, the floor is yours.
Excellent, thank you. Thanks for the introduction there. I'd like to take this opportunity as well to thank the organisers for such a great conference this week and for allowing me to share our work today. So, as mentioned, our work is for unsupervised one-class learning for anomaly detection on home IoT network devices. So I'd like to start off, give you some background about this. So, to improve our quality of life and well-being, many homes now incorporate a number of smart devices, including things like televisions, kitchen appliances, lighting, power switches, you name it, we seem to be connecting it to the internet at the moment. This is making home networks increasingly more complex and larger. And the smart home market is projected to show an annual growth rate of around 18% over the next 3 years, resulting in a market volume in 2023 of 139 billion US dollars, with a total of over 75 billion IoT devices worldwide by 2025. Each new device that we connect to our home network increases our security risk within that network itself. IoT devices can contain sensitive personal information such as usernames and passwords, and once compromised, they can be used to gain a foothold on the local network and be used as a pivot point to allow an adversary to attack other devices on the network, or be used as part of a botnet to attack other infrastructure on the internet. Manufacturers are keen to adopt consumer IT. With this being said, they can rush devices to market with a lack of security consideration. So many devices already have been reported to contain.
Sorry to interrupt, but would you like to share your screen?
Oh, thank you very much. Sorry
for the interruption.
That's all right. That's totally my fault. There we go. Okay, there we are. Can you see that?
Perfect. Yeah.
Excellent. So consumers will naturally expect home appliances to be operational for many years after purchasing them, and therefore is critical that support and security updates of IoT-enabled devices reflect the true life cycle of consumer ownership. Okay. So with an increasing number of devices on our network, it's becoming virtually impossible for typical home users to understand and characterize the activities being carried out across their own home network environment. And with the growing belief that cybersecurity is everyone's responsibility, offering improved security solutions for that home environment better enable all users to adopt a security as a culture. Now, how can we tell if devices are compromised? In a corporate environment, intrusion detection and intrusion prevention systems can be used, but these being deployed at like a network level or even a host-based level within the enterprise security solution. This consists of sort of static perimeter defenses such as firewalls, intrusion detection, and as I said, coupled with host-based defenses such as endpoint detection and response, antivirus, anti-malware, regular patching of software vulnerabilities. This enables us to have a good control of anomaly detection and malware within an enterprise solution. However, these are pretty unsuitable for deployment in a home network environment due to the complexity of the solutions, costs associated with expensive enterprise-grade software and hardware, and the ability of non-technical users to understand the outputs of these tools. So coupled with the fact that IoT devices are typically resource constrained, heterogeneous in nature, we need to look at new solutions of how to better prepare us for the novel security issues that these types of devices and the location introduces. So one way of sort of determining bad behavior is anomaly detection. And machine learning has become widely used for anomaly detection in a number of security applications, including network traffic analysis, malware analysis, and insider threat detection. Supervised classification models require training of respective classes. So we need to see malicious traffic, we need to see benign traffic and train our models using that. So that can pose real challenges in the security domain, since we may not have training examples of all malicious possibilities, and the number of benign samples may significantly outweigh the number of malicious samples available. So the vast majority of our home network traffic is actually going to be benign. So one approach to overcome this supervised classification issue is to train our model and learn from a single class. So using this model, we can actually check for deviations of normal behavior by looking outside of our classification of that benign traffic. So one way of doing this is the one-class support vector machine. This was developed to resolve training classification problems, which only has one type of sample. So the model can be trained solely with benign traffic to build a picture of what we determine as normal communication behavior of a device, and use this as our base for anomaly detection. So one-class support vector machine maps the input space into a high dimensional space by the kernel function. And the support vector machine for novelty detection by Skolkoff et al. Separates the data points from the origin and maximizes the distance from the hyperplane to the origin, which results in a binary function that captures regions in the input space and defines, as I said, it's a binary function. So the positive class in the region defines most of the data points, and a negative class would be the anomaly and lie outside of this main classification. So we wanted to look at related works, and there is some sort of work out here in these types of areas. So Median et al. Demonstrated that using network traffic analysis and network flow analysis, we can actually identify IoT devices on the network and separate these from regular sort of devices like your laptop and your desktop. So focusing on network flow traffic looks like a good solution. There is some other work for IoT anomaly detection, and including home network detection. So Anthi et al. And Eula et al. Had a couple of papers on this. Anthi et al. Proposed a supervised approach and demonstrated that a number of network-based cyber attacks, such as man-in-the-middle, denial of service, reconnaissance, and replay attacks could be detected. And Eula et al. Combined network flow analysis with supervised machine learning in order to detect IoT anomalies, but that wasn't specifically focused on home networks. There was some work on unsupervised intrusion detection, and Casas et al. Combined unsupervised models with network flow analysis and demonstrated great results here, but that was based on sort of regular network traffic and wasn't specific to IoT devices. So our work is taking all this on board. We propose the use of a one-class learning model for profiling home IoT network devices, and then use that model to demonstrate any anomalies in the network traffic. And we identified networking characteristics of these common home IoT devices, and then evaluated the ability to define both normal and anomalous network activity for such a device. And we presented this on a lightweight IoT profiling tool, both based on a Raspberry Pi Model 4, because the intention was, can we design something that non-technical consumers for a low cost can actually plug into their networks and use as part of a home defense system. So the initial research looked at a typical home network, including some IoT devices. So this was tested on the first author's home network, and specifically looking at 4 IoT devices: an Amazon Echo, a wireless network printer, the British Gas Home Hive set of sensors for your home heating and water sensors, and some Netgear Arlo CCTV cameras that upload its video to the cloud. Now, because this was on a home network, we had a Netgear switch that all traffic, including wired and wireless, went through, and then we port mirrored this back out to the Raspberry Pi so that the Pi could actually detect the and capture the required traffic. So with the packet capture, the IoT devices were detected using a combination of Mac vendor and service fingerprinting. Once we had identified the devices, we could then add these to the packet capture. The packet captures were rotated and processed every 60 seconds. And there was an initial training period of 48 hours, which we used to develop the normal traffic model. After that 48-hour, where we had the normal baseline, each subsequent 60-second capture was checked for anomalous behavior against the model. And because we also had this network profiling device, we could create some sort of interesting graphs to look at. And these were aggregated into 15-minute chunks and displayed. And we could look at things like sort of packet size, volume of data in and out, and also look at destinations. So what was the top inbound and outbound connections for that device over any period. With the data capture itself, we had a limited number of features that we extracted from the packet. This was heavily based on previous work that we had identified in our literature review. And talk at the end, there can be further work here to further refine this. But we looked at the sort of protocol, the source and destination IP addresses and ports, and then looked at the number of packets and the total number or total size of packets going in both directions. Because the traffic is often encrypted itself, we didn't look at any of the payload information from the application layer and just looked at the sort of header information here. So once the training period is complete, we took the pre-processed data, analyzed and removed any outliers and any erroneous records that were there, converted the IP addresses to decimal values, and then used the standard scalar functions from scikit-learn to remove any kind of variance from these. And we then passed the scaled data through principal component analysis to perform linear dimensionality reduction and reduce this to 3 component features. The types of attacks that we looked at initially were quite limited. Recent studies showed that IoT devices have been compromised to form denial of service attacks on the internet. So thinking of like the Mirai botnet. So we focused initially on looking at seeing whether we could detect denial of service easily. So we looked at 2 different types of denial of service traffic, TCP SYM flood and UDP flood, and used HPing3 to inject these attacks into the network. Now, literature has shown that the common duration for denial of service attacks is around 90 seconds. And they do that to try and avoid detection. So that was what we limited our attacks to. And here we can see the a graph with the sort of balance of training conversations versus the denial of service conversations that we had. So to evaluate the performance of this, we need to think of some of the evaluation metrics. So we have our true positives that were conversations that were predicted as being benign when they are actually benign. True negatives are the conversations predicted as malicious when they're actually malicious. And then we have our false positives and false negatives. This in itself sort of gives us an indicator, but we can look at some other metrics based on these. So we have accuracy, which can be used as a measure of performance, but accuracy doesn't tell us the full story when we're working with class imbalance data set. So think about if 90% of our traffic is benign, a classifier can achieve 90% accuracy by saying all of this traffic is benign, whereas in reality, it failed to detect 100% of the malicious cases. So 90% accuracy is just completely misleading. So this is where precision and recall and F measure come in. Precision answers the question, what proportion of conversations that we identified as negative were actually negative, whilst recall attempts to answer what proportion of actual negatives did we identify correctly. So when we take these together into the F measure, we can provide a single weighted metric to evaluate the overall classification performance. And an F measure of 1 is perfect precision and 0 is terrible. So looking at our results from this model, on the left-hand side, we've got the confusion matrix where we're looking at our true positives, true negatives, and false positive, false negatives. And on the right-hand side, I've got the output from the accuracy, precision, recall, and F measure. So looking at the F measure there, the devices range between 92% to 99% of traffic, indicating that this was highly effective at detecting denial of service attacks. We also took a look at the graphs that the network monitor produced over on the right-hand side here, and we can see that there is a distinct difference in the volume of data, the average size of data, the average number of packets in a conversation, and the average amount of data within that conversation as well. So it does indicate that looking at just these sort of basic network flow statistics, we can actually detect this. On the left-hand side, I did a plot of the clustering reduced to 2 dimensions, which kind of showed some interesting results there, that the outlier is the big long red lines, and the benign traffic is the sort of blue traffic, the blue dots there. So for most of the devices, that was heavily clustered in one place, and the Amazon Echo was a bit more all over the shop. So in summary, a Raspberry Pi using the Python Scapy library that we were using for packet processing was good at processing traffic from low bandwidth IoT devices. But when it tried to process captures of greater than 2.5 meg in a 60-second capture, it was really starting to struggle. So this would impact things like Amazon Fire Sticks, where you're streaming 4K TV. But when we did look at low bandwidth IoT devices, the one class support vector machine classifier is highly effective in detecting this type of denial of service, or these types of denial of service attack. Looking at the actual stats there, the packet length and the number of packets in a conversation were great indicators of malicious behavior. So the packets would be significantly smaller than normal. And a major limitation of using this type of approach of having our 48-hour window where after detecting a new device, we treat it as behavior. That absolutely means that if you plug in a compromised device to your network, we will treat the malicious behavior as normal. So that's not great. So what is future work? One of the things that we can kind of look at is creating maybe sort of canned base profiles for popular devices like Amazon Echoes and the more well-known IoT devices. We need to look at exploring feature selection. So IP addresses were one thing that we were looking at, but with an Amazon Echo, for example, streamed music from thousands of different Amazon server addresses within a short period. So maybe looking at ASN instead of an IP so that everything is coming from Amazon, maybe something that would improve this even further. We obviously need to expand the types of attacks and devices under test. And we should also give consideration of how do we present this information to non-technical users and what do they do with it? I mean, it's all well and good designing something to detect issues on a home network, but if we can't convey this information usefully to a non-technical user, then what's the point? So research needs to also look into how we do that. So that was everything. Do we have any questions?
Thanks a lot, Jonathan, for this brilliant presentation. That's very interesting.
Thank you. And sorry for not sharing for the first slide. It's
actually, it was very interesting even without the slides. So well done.
You didn't miss any slides other than the title. So.
I have a couple of questions from the audience. So the first from Anika. So thanks for your presentation. There are so many connected devices around nowadays. So I was wondering what, if any, connected devices you would never allow into your home?
That's kind of interesting. So yes, there are a number of, as I said, like at the start, there are some perhaps IoT devices rushed to market. Some of the things that I've looked at include some smart switches from some manufacturers that you may have never heard of from the Far East, for example, that you can get very cheaply on eBay. Looking at one of those, for example, and how it actually does its command and control of being able to switch your plug on and off, it basically just blew a big hole through your home router firewall and connected to an IRC channel, so Internet Relay Chat. And if you could compromise that IRC channel, you have access to thousands of devices worldwide. That one didn't stay plugged into my network for very long. So, I mean, I would say it's not a guarantee, but try and stick with larger manufacturers that actually consider security as important for their IoT devices rather than just something you've never heard of is a good start.
That's fair. We have a couple of questions from Dr. Cyril. So the first one is, John, great work and presentation. As part of the future work, it would be interesting to investigate payload data, since some attacks embed C2C in the payload. Oh, that's
Yeah.
not. And so the question is, secondly, did you capture both data packets and flows? If not, what is the rationale for not considering flow information?
So we didn't look at payload specifically, and that was because a lot of the more reputable IoT devices that was actually testing here, the payload is encrypted. So we can't really get anything useful out of that. So instead of trying to look at specific cases where it was unencrypted or whatever, we wanted a mechanism that would work for all of these home IoT devices. So I mean, we looked at the data flows with respect to the main headers up through to TCP layer. So predominantly looking at IP and TCP or UDP headers to actually gain information for every device rather than, as I said, unencrypted ones.
Perfect. I have a couple of questions, if you don't mind.
Sure.
So, will you make your data set publicly available? Are you planning on publishing the data itself?
Yes, I think, actually, I was trying to think whether there is a reference to it in the paper. I'm not sure there actually is. Yes, we probably should make that data available. Absolutely.
Specifically that there is a lack of IoT data set for
yeah. So in the paper, there's actually a bit where I talk about this, where I looked at existing data sets, and they're either supervised, labeled
or
data
old,
sets,
or very old, or
older, or looking at things like regular network traffic, so including things like computers and desktops. And we didn't want to look at that because IoT devices, part of the nature of their traffic is they're very constrained in the servers that they're talking to generally. So it is a completely different network flow compared to a regular desktop, for example.
Right. Well, we have a question from the audience, so that's a higher priority than mine. So from Andrew, do you think the approach could detect compromised devices participating in DDoS, or which were being abused for crypto mining?
Sorry, I didn't quite get the question. So it was, could I detect crypto mining? Was that the?
Yeah, could detect compromised devices participating in DDoS, or which were being abused for crypto mining.
Okay, so yeah, I think it definitely could be used to detect crypto mining as well, because you're, I mean, by looking at the IP addresses, one of the things that really stands out is an Amazon Echo only talks to Amazon servers. So if you're suddenly talking to some Chinese server and sending results from crypto mining to other servers, that then does start standing out. And again, the normal traffic for an IoT device is very consistent with packet length, packet sizes, packet regularity. So I think those types of indicators would massively stand out. And yeah, it's probably something, as well as attacks, that's something that we should be looking at for our future research.
Right. So one last suggestion / question. Would you consider to generalize your model to not include IP addresses in the feature list?
Yeah, so that was one of the things that I kind of mentioned about whether we can actually look at maybe ASN and rather than IP, because one of the things we kind of noticed is like Arlo always talks to the same CDN, like Amazon pretty much always talks to the same CDN. And so actually dropping the IP address and having it as a more generic, like, where is this an Amazon server? Maybe that would help. So yeah, it's something that we definitely want to explore going forward.
Perfect. Thanks a lot for the interesting discussion. I mean, we can keep on.
Thank you for all the interesting questions too.
Yeah. we have a last very quick question from Dr. Cyril. So would you consider conversational agents, say voice versus data detection, since some home IoT can be triggered by voice?
Yeah, that is a good question. So we haven't actually, as I said, broken it out based on sort of what the payload is. It's really who are we talking to. So stuff like triggering an Amazon Echo sends that data off to Amazon to actually get the response. So yeah, we're not really, or we haven't as yet sort of like made that distinction between normal sort of traffic and voice traffic. But yeah,
Perfect.
I think it could work. Thank you very much.
I would encourage everyone to take further discussions to the forum. Very interesting discussion, very interesting presentation, Jonathan. So thank you so much.
Thanks very much for having me.
We'll be starting the next presentation in just less than 5 minutes. So I'm looking forward to seeing you all there. Thank you.
Okay, thank you.